So good evening everyone. I hope I'm audible. So before I begin today, I have some announcements to make. So currently I am not in my campus, so I'll be low in bandwidth. If you see that my internet is not good, you can just inform me. Okay, and next week we'll not have any lecture. So the next Sunday will be off, and I'll take some extra classes um, after Diwali. Okay. Am I audible, right?
Yes.
Okay, thank you. So what I have planned for today is we will discuss the solution of assignment 1, and assignment 2 is also live. You can be able to see that assignment 2 right now. So I'll discuss assignment 2 as well, and then we'll move on to uncertainty, specifically introduction to probability. So we'll talk about, so for in today's class we'll just talk about probability. All right. So before going to today's class, as we discussed, that we'll talk about the solution of assignment 1. So I have already uploaded the solution to assignment 1. I'll just have a brief discussion of the solutions. So I have given two functions. One is DFS and the other is BFS. Okay. So you can use either of those. So if you want to implement DFS, you can call this function DFS, and if you want to implement BFS, you can call BFS. So I have not specifically used any inbuilt, or you can say any library which will help you store data like stack or queue. I have just named stack and queue for each list. So I'm using list. All right. So this function DFS takes three inputs. First is the maze, second is a start position, and the goal position. And the maze which I am representing over here is a list of list. So if you go down, you will see this maze is actually a list of list. All right. So this is how a maze is represented. And so what I'm doing is I'm storing the start position in the stack, and I'm keeping a set visited. So this will help me keep track of all the positions which I have already visited. And if I have already visited that cell, then I'll not go there, because unnecessarily it will create more iterations. All right. And this parent variable is actually a dictionary in Python, which is allowing me to store the parent of the current node. So currently I only have one node, which is start node, and it doesn't have any parents. That's why I have labeled this as none. This while loop, what it is doing is it is checking whether the stack is empty or not. So when I say while stack, it checks if the stack is empty or not. If it is empty, then it will return false, otherwise it will return true. Therefore the while loop will execute, because currently in the stack I have one node. What I do is I pop. So when I pop an element from the list, it actually retrieves the last element from the list. So currently my list has only one element. It will get deleted from that list, and it will be stored in current. Now this will check if the current which I have, the position which I have stored in current, is it the goal or not. If it is the goal, then it will call this function reconstruct path, and whatever the reconstruct path function will return, this DFS will then return. Okay. Now I am storing this current because I have already visited that node, current node. Now what I'm doing is I'm calling a function called get neighbor. We will see what this get neighbor does. It actually gives the neighbors of the current node, and for each of those neighbors I'm iterating over those, and I'm seeing if it is not visited, then I am storing the parent. So current is the current node, and I'm saying this neighbor has a parent which is the current node, and I'm appending it to the stack. So this stack will take care of the DFS. I don't need to bother about how the DFS is working, because I am already doing I am already using the data structure stack. All right. And this will be executed for all the neighbors. And if I will not be able to find any node which is the goal node, then this function will return false. Now we'll see how this reconstruct path works and get neighbor works. So first let us see what get neighbors does. All right. So get neighbors, it takes the maze and the current node, and I have given directions. So it has 4 directions. Either it can go right or left, up or down. And I'm saying currently the neighbor is empty. And what I'm doing is this current has 2 elements in it, the X position and the Y position. So I am just assigning it to X comma Y. So this is how you can do it in Python. You will not be able to do the same syntax you will not be able to use in other languages like C++ or Java. This is Pythonic way to do it. Now what I'm doing is I am extracting the size of the maze. So how many rows are there and how many columns are there. So this will give me the number of rows, and this will give me the number of columns. Now I have 4 actions I can take at that node. So what I'm doing is I have 2 variables, dx and dy. So either X can be incremented or Y can be incremented. So what I'm doing is for each element in direction. So this is the first element, this is the second element, third and fourth. So in computer science, generally it is written as 0th position, first position, second position and third position. In the 0th position, I have an element which is 0, 1. So that is what I'm saying is dx, dy. And I'm saying the next X and next Y, what will it be? It will be X plus dx and Y plus dx, dy. Now what I'm doing is I'm checking whether this new position is feasible or not. How will we check? So we'll see if this new position has to be greater than equals to 0 and should be less than row. So why I'm doing less than? Because this length will actually give me 1 extra. So in this case I have only, so this is I'm labeling as 0, 1 and 2. but when I call length, it will give me 3. So I'm saying it should be greater than equals to 0 but less than 3. And similarly, I am checking for column as well. Moreover, I have to check if there is any wall or not. So this condition is checking whether there is a wall or not. If in the maze I will pass the position of x comma y, if in that position I have a 0, then I can move to that position. And when that happens, I'll say I have found a neighbor which is next x comma next y, and I am storing it in neighbor. In this way, this neighbor list will get populated and it will be passed to the wherever the function was called. So where the function was called, the function was called over here when I am calling get neighbor. All right, and this loop in DFS will iterate over all the neighbors which this get neighbor function is giving. Okay, so this is how get neighbor works. Now how this reconstruct path works, what it is taking in as input, it is taking the dictionary parent. So what does this dictionary have? It has a node and its parent. All right, so I am passing the dictionary to this function. I am passing the start position and I am passing the current position, but you see this current is actually the goal. That is when this if statement will be true. Therefore this current is actually the goal. Okay, so this reconstruct path function gets the dictionary of parents, the start position and the goal position. What does it do? It creates a list which is path and empty list. It is an empty list. Now you see we had stored none as the parent of the start node. So whenever I encounter a node which has a parent none, then I'll know that I have reached my starting position. All right, so this will help me in a way. So what I am doing is, if current is not none, so it is checking if this current which I have, so over here I have passed current as the goal. So if this goal is not none, obviously the goal is not none, it will do path dot append, it will append the current node, and I am updating the current node as the parent of the current node. So this is how equality work over here. So this is not the mathematical equality, this is an assignment. What it is doing is, for the current node, which is actually the goal right now, it will check what the parent of this goal node is, and it will store the parent in the current node. Now in the next iteration, this current is what? This current is actually the parent of goal, and it will check if this current is none or not. If it is not, then it will append that node to path. And again, for that node, it will get the parent and then it will check whether it is none or not. In that way, you will create an direction which is opposite to the path which you want. It is in the opposite direction. You are starting from the goal and reaching the start position. Therefore, you have to reverse it. So this is a way to reverse it. And by the way, I want to take one more tutorial class on Python. So after Diwali, I'll take one more tutorial class on Python. In that way, those of you who are not familiar with Python will be able to understand this syntax. So at last, this path is actually storing the path in the opposite direction. So I have to reverse the direction and then return the path. Okay. So what this DFS is doing is, it is calling this function, and this function will return the path in the correct direction from start to goal, and then this DFS will return the path if it exists. If it doesn't exist, then this DFS will return false. This BFS works in a very similar way as the DFS is working. The only difference being, over here, this visited is updated once I have a node current. But in BFS, I am updating this visited when I have a neighbor. So this actually is coming from data structures knowledge. If you don't understand that, it is not important right now. Okay, so everything else remains the same, and one more change is we are using a queue. Therefore, we are popping from the first position, and hence the algorithm BFS is working. Everything else remains the same. Any questions? Okay, so I guess this solution is clear. So if you go to Google Classroom right now, you will be able to see that there is one assignment which is live, and this is assignment 2, and this is on logic. So this is a very simple assignment which I have given you. There is no algorithm which you have to implement. The goal of this assignment is to make you understand that you will not be able to code everything, and that is why you need an agent which can take decisions on their own. So what this assignment teaches you is that it will give you some knowledge base. So it will give you some knowledge base, and it will ask you for some query, and you have to give a function for each of those queries. So for example, there are some symbols: is day or not. So it will give me true if the time of the day is day, or if it is night, then it will be false. Is it raining or not, if someone is home or not, and so on and so forth. So these are the symbols. So one function can be, should I keep the lights on or off in the living room? So what does it check? It checks if it is daytime or not, and if someone is at home or not. If that is the case, then keep the lights off, otherwise keep the lights on. And this is one function. So imagine if you are making an agent and you are defining multiple functions to do these tasks, you'll not be able to enumerate all possible functions. Okay, and that is why the concepts which we learned in the previous class, which was resolution and then inference, that helps an AI agent to come up with rules on their own. You don't have to specify your own functions for each and every situation. You'll not be able to do it. So I have multiple functions which I want you to implement. One function is heating system. So this function takes input what is the current temperature and if someone is at home or not, and it will tell you whether to switch on the heating system or to switch it off. Security alarm, garden sprinklers, and there are multiple functions I have given you to implement. These are very simple functions. What you have to do is you have to take inputs, check whether it is true or false, and this is the condition when the heating system should be on. So you have to give us if statement, and you will have to check the condition for these two symbols, and then you have to return true if you want the heating system to be on, and you have to return false if the heating system should be off. And these are the 4 functions you have to implement. You have to test for multiple scenarios. So these are different scenarios. Okay, and then I have given you one more task which calls, so this is a function which calls another function. So you see this evaluate energy savings, it is calling another function heating system. So it is checking if heating system is on or not. It is checking if living room lights are on or not. It is checking whether garden sprinklers is on or not. And then for all this, it is passing it to this function. If all the 3 things are off, then the house is in energy saving mode. So it is returning, yes, everything is off and the house is in energy saving mode. So you see this function is actually calling multiple functions and then performing a task. Okay, so these are like compound functions. And I have given you another this is an example, and using this you have to write your own function for maybe counting of number of active systems. So you will be able to do it. It is not very difficult. Okay, and then this conclusion is important. What does it say? It says that when you implement these tasks on your own, you will realize that you will not be able to implement all the scenarios that can happen in any setting. Therefore, you need these kind of algorithms which we are talking about right now, such that the artificial intelligence agent can do tasks on their own. Okay, so this is what assignment 2 is all about. Any questions?
Shubham, are we supposed to take constraints into consideration while solving the solving the assignments? Means just like uh, check whether a light is on or off. If there isn't anyone, are we supposed to consider the means, for example, atmosphere is cloudy, so are we supposed to consider such kind of constraints?
No. So these are the only inputs you have to take, whether it is daytime or
Okay,
not. That is,
okay. Okay, these are the only inputs. Uh,
yes. This
okay,
assignment is actually a complete. I guess there won't be any question if you go through the assignment once. Okay. In
okay.
case you have questions, you can post it in the forum.
Sure.
Okay. Okay. So we will begin with uncertainty. And today we will not talk about any algorithms or implementation of AI systems which does decision making in uncertainty. Today is all about introduction to probability. So those of you who are not familiar with probability will benefit a lot from today's class. And another thing is, why are we talking about uncertainty? So you see in the previous class, so if we go back, so what is the situation? We had a knowledge base and we had a query. And what was the thing we are looking about? So we were looking about that we have some knowledge base and the answer that we were looking at is whether the query is true or false. But this is not always the case in every scenario. So we can have an answer like this also. So this query, we are confident 95% of the time will be true, or because of some uncertainty you will not be able to say for sure that 100% of the time it is true and 0% of the time it is false. It will be false with 100% probability or true with 100% probability. So there can be some uncertainty. So for example, you will be able to say that this query will be true maybe with 90% probability. So for example, I have some knowledge base. For example, I have the data of past weather records of a city X, and I'm asking you a question whether there will be rain tomorrow or not. So this query, you will not be able to say with certainty. You will be able to say like this, that tomorrow might be a rainy day with 90% probability or something like that. So this is why uncertainty comes into picture. So every time you will not have a deterministic environment, you will have to have consideration of stochastic environment. So for example, I have a robot. So you can take Mars rover. So whenever Mars rover is going, it doesn't know what it has in front of it. It takes input from various sensors, and those sensors reading they have to evaluate. Now they are not 100% sure what they are seeing is the thing they are imagining, so they have to take some probability. Okay, this looks like a water, or maybe this looks like a big rock. So there is some uncertainty that it might not be a rock, because it is not actually knowing what it is. It is taking an image and then processing it. So there is some uncertainty in its mind, and it has to take care of that uncertainty as well. Okay. So this is where we have to make our models such that it can handle uncertainty. Okay. So this is some introduction of why uncertainty is important. Shall we proceed? Okay. So we'll talk about probability. Now I'll go to the basics of probability. So you might find this lecture a little bit not related to AI, but I want you to understand that probabilities, discussing about probability is not very difficult, because when I was in class 10th 12th, I found this subject to be difficult. So I don't want you to think like that, because this is a very intuitive subject. Okay. So I'll go into a little bit deeper. I'll not talk about a lot of mathematics, but I'll talk about various concepts. So bear with me for today. Okay. So before talking about probability, we have to understand what is a random experiment. And today I have not made any slides. I'll just write everything on my own. So, and I will provide the slides which I am preparing today. Okay. So everything will be handwritten today. So we'll talk about what is a random experiment. Okay. So what is a random experiment? An experiment whose outcome cannot be predicted with certainty. So you have an experiment whose outcome you will not be able to say with certainty. So for example, if I toss a coin, this coin toss, you will not be able to say whether the outcome will be a head or a tail. So there's a term outcome. So this is the building block we will build upon. Okay. So an outcome is an individual element we are talking about. Okay. We will build upon this term outcome. So this coin toss is an experiment, And why it is a random experiment? Because the outcome of this experiment is uncertain. You don't know whether it will land on a head or a tail. Okay, so this is one example of a random experiment. Another example can be, so for example, you are reading a book. So the time it, that you take to read the book is also uncertain. So you can read the book in a minute, you can read the book uh, in an hour, you can read the book in a month, you can read the book in 10 years. Maybe you didn't complete the book at all, so you took infinite amount of time to read the whole book. So this is also an random experiment where the outcome is uncertain. Okay, so these two experiments fall under this uncertainty in this experiment. So we have uncertainty, right? This uncertainty in this experiment is because of inherent uncertainty. So the outcomes of this experiment are inherently uncertain, but there can be another kind of uncertainty as well. What is the second kind of uncertainty? The second kind of uncertainty is due to lack of knowledge. So for example, if I ask you what is my birthday, so this, there is uncertainty in your answer. You will not be able to say with 100% sure what will be my birthday. Why? Because you don't have the knowledge. There is nothing inherent uncertainty in that, because my friends and family will be able to tell me that this is the day you were born, but this knowledge is not known to you. So this kind of uncertainty is due to lack of knowledge. So there can be inherent uncertainty, or there can be lack of knowledge. Because of these two things, there can be uncertainty in any environment. And we have understood what is a random experiment. Okay, now we'll talk about sample space. So these are the two concepts for now: random experiment and types of uncertainty. The next concept which we'll talk about is sample space. And by the way, how many of you are not very confident in probability? You can just raise your hand. All right. Okay, so we'll talk about sample space. So what is a sample space? Sample space is just the collection of all possible outcomes. So you can have multiple outcomes of an experiment. So the collection of all possible outcomes is known as sample space. So for the coin toss experiment, what are the different outcomes? So I will write the sample space as S. It can be written as omega as well. So currently I'm writing as S. So what is the outcome of a coin toss? It can be either head or tail. So these are all possible outcomes of this experiment, which is a coin toss. Therefore, this is the sample space of this experiment. What is the sample space of this experiment? Reading a book. So what is the time it takes to read a book? The sample space over here is continuous, and it can be in between. So suppose I am saying, so let it be not 0. So I'll just erase it. So what I say is, this is between 0 comma infinity. Okay, so it says that you can take a time which is, so this is an open interval. So it says that it might not be 0, but it can be as close to 0 as possible, and infinity because you will not be able to read the book at all. So you left the book unread, and we are saying that the time it took to read the book is infinity. So this is another kind of sample space where it is a continuous interval between 0 and infinity. Okay, for this birthday experiment, when I'm asking you a question, in such case, the sample space is actually any day between 1st of Jan to 31st of December. Okay, it is this. Now sample space can be of different types. So I'll just write it over here, sample space. So sample space can be of different type. It can be either countable or it can be uncountable. So what is a countable sample space? Countable sample space are when you are able to count the individual outcomes of the experiment. So over here you see there are only two outcomes, head or tail. So you are able to count this outcomes. Okay, so this is a countable sample space. What is an uncountable sample space? any interval. So you suppose, for example, 2 to 0. So this interval is an uncountable sample space. You'll not be able to count the number of outcomes in this experiment. Okay, so this is an uncountable sample space. Now you can further classify these sample spaces into further categories. Countable sample space can be of two types: finite and infinite. So for example, this coin toss is countable finite sample space. Why? Because you are able to count head, tail. So there are two outcomes. Moreover, it is finite because it only has two elements in it. You can also have countable infinite sample space. So for example, let us consider an experiment. So what is the experiment? Tossing a coin until head appears. So what will be the outcomes of this experiment? So is this an outcome head? You see, you are tossing a coin and in the first toss only you get a head. Yes, this can be an outcome of this experiment. You can have tail head. Why? Because in the first toss the outcome was tail and in the second toss you had a head. So this can be one outcome of this experiment. Similarly, you can have tail head. Why? Because you are stopping the experiment once head appears. So in the first two tosses you had tail, but in the last toss you had a head, and so on and so forth. You can have th, and so on and so forth. So you see, in this experiment you can have infinite elements or infinite outcomes of this. So this is the sample space, and in this sample space you are able to count. You see, this is first, this is second, this is third and fourth, and so on and so forth. So this is a countable infinite sample space. Is this all right? Okay. So I was talking about uncountable. So this can be further classified into bounded and unbounded. So bounded is this. So you are saying bounded experiment. So for example, you take an experiment where the time you took, for example, time you took to take a test of 2 hours. So the time limit of the test was 2 hours. So what will be the time? So this will be the sample space actually for this experiment. You can finish in 0 minutes and you can take 120 minutes, right? So you are saying this is an uncountable bounded sample space. Why uncountable? You can minute down to seconds, milliseconds, and so on and so forth. So you're not able to count the elements or outcomes of this experiment, and it is bounded because after 2 hours there is no feasible outcome for this experiment. An unbounded uncountable sample space is the first example. So for example, over here we talked about the time it took to read a book. So I said it can go to infinity. So because you are not reading the book, you just left it unread. In that case, you are taking infinite amount of time to complete reading the book. Therefore, this experiment has an uncountable, unbounded sample space. So the sample space for that experiment was 0, infinity. It is uncountable and unbounded. Okay. So these are the different classifications of sample spaces. Okay. Now we'll move on to events. What are events? So events are collection of outcomes or set of outcomes, you can say. Set of outcomes. So for example, there is an experiment. What is that experiment? Toss of 2 coins. So for toss of 2 coins, the sample space will be head head, head tail, tail head, and tail, right? You can have events. So what can be an event of this sample space? You can have at least one head. So head head, head tail, tail head. This is an event. You can have another event, both same. So A1, I can say A2, both same. So head, head, tail, tail. This is also an event. You can have two heads. So this is also an event. Okay. In this way, you can have multiple events of a sample space. And for your knowledge, I'll tell you that there can be a null event as well. In null event, there is no outcome. Okay, so this is also an event. So what is an event? Event is a set of outcomes. Now, when we are talking about probability, we are interested to find the probability of an event on the sample space we are talking about. So first we'll talk about what is the experiment, what is the experiment which we are doing. Second, we'll see what is the sample space. I'll write just SS. And third, we'll talk about what is the event of interest. When we have these three, the experiment which we are doing, the sample space which we have, and the events which we are interested in, then you can go on or move on to talk about what is the probability of occurrence of that event. Okay. Any questions? Now, I talked about this sample space, right? So for one experiment, so for example, this experiment tossing of coin until head appears. So we are interested in this experiment. Now the sample space of an experiment can be written in multiple ways. So it is not the case that the sample space is unique. You can have multiple different sample space for the same experiment. So you see this is one sample space, right? Where I had head, then tail head, tail tail head, tail 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 head, and so on and so forth. This is one sample space. I can have another sample space. So I'll just say S1. S2 can be 1. So I'm talking about the number of tosses you did to reach the first head. So it is 1, 2, 3, 4, dot, dot, dot. So you see this and this represent the same experiment. But the event of interest can be different. Over here, we're talking about the number of tosses it took to reach the head. Over here, we're talking about exactly what are the outcomes of those tosses. But these two sample spaces are of the same experiment. So why I'm bringing this up is because an experiment can have different sample spaces as well. Okay. So this is the point I'm trying to convey. Now, is this all right? Now we'll talk about an important concept in probability, which is known as before that, some concepts of set theory. So when I say A union B, and if you go to the Venn diagram, so it says that this is A, this is B. A union B is actually the set of all the outcomes that are in B, that are in A, or that are in B. Okay, so this union is actually OR. We were talking about that in logic. So in union is OR. When I say A intersection B, then this intersection is actually AND. So the outcome should be in A as well as in B. Okay. Now I can have complement. So if I have A, then I can have A complement. So this complement can be thought of as negation. So I talked about A, not A. So this complement is similar to negation. Okay. And then we talked about De Morgan's law as well in logic. So what was De Morgan's law? I said that A union, sorry. A union B complement. So De Morgan's law says that you can take the complement inside, which will be A complement intersection B complement. So these are some of the rules in set theory. And in logic, we talked about this as negation of A or B. So this we had written as not A and not B. So these two are very similar things. Okay. Then we can have like this also. So I have A union B intersection C. We talked about this as well. So it will be A intersection C union B intersection C. Okay. And in a similar way, you can have also A intersection B union C, which is written as A union C intersection B union C. Okay, so these are some of the rules. Now there is an important concept of sets, which is disjoint sets and exclusive, mutually exclusive sets. Disjoint. or mutually exclusive. Both are same, mutually exclusive. What does it mean? It says that disjoint sets, suppose A and B are disjoint sets, it means that there is no outcome or elements common in A and B. Okay, that is when we say A and B are disjoint. So in Venn diagrams terms, if this is A and this is B, if this is A and this is B, then this is empty. There is no element over here. There is no element over here. Okay, that is the case. Then we will say A and B are disjoint. Therefore, we can just draw this is A and this is B. Okay, so this is about disjoint or mutually exclusive. There is one more concept which talks about collectively exhaustive. So what is collectively exhaustive? It means that if you have two outcomes, two events A and B, two events A and B, and if you take the union A union B, then this will become the sample space. When you have, so you can have multiple events as well. So suppose you have A, B and C and you took the union and it became the sample space, then you will be able to say that A, B and C, these three events are collectively exhaustive. Okay, so this is mutually exclusive and this is collectively exhaustive. So now tell me, A and A complement, are these two disjoint or collectively exhaustive or both? You can just unmute yourself and speak. A and A complement. I have two events, A and A complements.
Both.
Both, right? So you see why they are the disjoint, because there is no element common in A and A complement. Why are they collectively exhaustive? Because A complement comes when you take out the elements from the sample space, the elements of A, then you will get A complement. Therefore, it is both disjoint and collectively exhaustive. Okay, so these are the two important concepts. Now we will, okay, just a minute. Okay, now what will we do is we will go to probability. So what is probability? So we have talked about events, and you see these events are actually sets. So this A, B are sets, right? Now, and these events are also sets because it is set of outcomes. So events are sets. Now what is probability? Can you tell me what is probability? You can just unmute and speak. What is probability? Okay, so you see, what is probability? Probability is actually a measure of uncertainty. Measure of uncertainty. Okay, it is actually a function. Okay, so it is actually a function. It takes input events. It takes input events, and what does it outputs? It outputs a number between 0 and 1. Okay, so what is probability? If somebody asks you, you can just tell them that it is a measure of uncertainty. It measures the amount of uncertainty there is in an event or associated with any event. Okay, and in mathematical terms, it is a function which takes the input, the events, and the output is actually a number between 0 and 1. Now, this function has to satisfy three conditions. Only then this function will be a good measure of uncertainty, or not good, appropriate measure of uncertainty. So you see, what I'm talking about is, this is a function, right? So you can have any function. You can say that event A is the event. So I'll say A square plus 2A cube. This is a function, right? So you cannot just say that this is the function of probability. No, if you are giving a function a measure of uncertainty, this measure has to satisfy three axioms, the axioms of probability. Okay, if any function f of x, if any function satisfies these three axioms, then it qualifies to be a measure of probability. So what are the three axioms? So if I say p of a is the function, if I say p of a is the function, then p of a has to be greater than equals to 0. So it cannot take negative values. It can take 0 values or positive values. The second is p of omega or S, omega is the sample space, or S, you can write S as well. This has to be 1. Okay, so these are two axioms. The third axiom, so these two axioms are obviously very understandable. Okay, you cannot have a negative probability, so it says that you are giving any function and you are saying that function should take value which is greater than equals to 0. You can understand this, it is very intuitive. Then I say the probability of the whole sample space has to be 1. Obviously, because you are taking the whole sample space, then any event in that sample space will occur, and therefore the probability of the sample space is 1. The third axiom says that probability of A, okay, just a minute, probability of A union B, this is given by probability of A plus probability of B when A and B are disjoint. This is the third axiom. What it means is, if you have an event A and an event B, if you take the union A union B and these two events are disjoint, then you can just sum up the probabilities. You can just take probability of A plus probability of B. Okay, this condition has to satisfy. Okay, when these two events are disjoint, then probability of A plus probability of B will be probability of A union B. If any function satisfies these three axioms, then it will qualify to be a measure of it will qualify to be a probability function. Okay, now you may ask me, why are you giving me why are you telling any function? You see, there are multiple ways to measure probability. What are the different ways to measure probability? There is a classical measure. There is a frequentist measure. And there is subjective measure. Sorry, subjective. So you see, in your in our school, we were talking about probability of A is what? Probability of A is the number of elements in A by the number of elements in the sample space. So for example, if I take a coin toss, when I say I have a coin toss and the sample space is head, so suppose two coins are tossed, then I have head head, head tail, tail head, and tail tail. And then there is an event A which says at least one head. So we'll have head head, head tail, tail head, right? Now what is the probability of A? In this case, you will say 3 by 4. Is it correct? Is this correct? Right. Again, I'll not tell you is this correct or not. I'll just give you one more example. So suppose there is second experiment where the sample space was head and tail. So I just have one coin and it gives me either head or tail. Now I'm interested in the event of head. So what is the probability of this event? Is it 1 by 2? Is it 1 by 2? Because I have one element in A dash and there are two elements in the sample space. So is it 1 by 2? You see, this measure, when you are saying it is 1 by 2, you are assuming some things in your head, and that might not be correct. You are actually applying classical measure. Okay, so what are you doing? You are saying what is the size of A dash? I'll divide it by the size of sample space. But this is only true when certain assumptions are met. So over here you are assuming that it is a fair coin. If it is not a fair coin, if it is biased coin, suppose you have a coin where one side is heavier than the other, then you will not have probability of head as half. It can be less than half, it can be more than half, but it will not be exactly half, right? Because it is an unfair coin. Therefore, this measure has some assumptions. Is this clear that this you will not be able to do if it is an unfair coin? Right? So classical measure has assumptions. It has two big assumptions. We'll talk about the first assumption. The second assumption will come when we discuss more. So what is the first assumption? So every outcome in the sample space, every outcome in the sample space are equally likely. So all the outcomes of the sample space are equally likely. So you are telling me that the outcomes head and tail are equally likely. So the probability of occurrence of head is same as the probability of occurrence of tail. In that case, you will be able to do this. Probability of A is actually the size of A by the size of the sample space. Okay. So this is how you will be able to apply the classical measure. So what does classical? So I'll come to the second assumption before that. So what is probability of an experiment of an event? It is size of A by size of the sample space. When, so we talked about different kinds of sample space. So this is when the sample space is countable, right? When the sample space is uncountable, I'll give you one example. So it will be size of A by size of S. So for example, there is a dartboard, right? So there is a dartboard, and I'll ask you what is the probability of hitting this area. So how will you calculate? First, you have to assume that all the points in this dartboard are equally likely to be hit by someone. Okay, so all the outcomes. So what is an outcome in this experiment, by the way? Any point will be an outcome in this experiment. So if I'm hitting any point, so suppose I'm hitting this point, this is one outcome of the experiment. There can be multiple outcomes of this experiment. Okay, so the sample space of this experiment is uncountable. There are uncountable number of points in this dartboard. Therefore, this is an uncountable sample space, but bounded, because the number of so all the points will be bounded by this outer circle, right? I hope you know what a dartboard is. So there is one board where we, yes, okay. So what I was saying is, so this is a uncountable but bounded sample space. In this case, you see, when we are asked to find the probability of hitting this area, what you will do is you will say area of A by area of the sample space. So this is how you calculate when the sample space is uncountable. Okay. So this is when the sample space is countable. This is when the sample space is uncountable. So we are talking about the classical measure, and it has a second assumption. What is the assumption? Is that the sample space is countable, finite, and uncountable, bounded. Why? Because you think that if the sample space is countable and infinite, so the size of the set S will be infinity, and the probability of that event will become zero, right? So for example, this experiment where we were tossing a coin until head appears. So the size of the sample space or the number of elements in S was infinite. And if you try to find out the probability of an event, for example, a head, will be zero. The probability of the second outcome will be zero. The probability of the third outcome will be zero. And each outcome will have probability zero. Now, the axioms of probability tells me that the probability of the sample space should be 1. But you see, all the outcomes of your experiment has a probability of 0. If you add all those outcomes, you will not get 1. Therefore, this classical measure is not applicable if you have countable infinite. Similarly, if you have unbounded, so if you have an unbounded sample space, this denominator will be infinity. And in that case, the probability of that event will be 0. And you will not be able to apply classical measure. So classical measure has two big limitations. Whenever your sample space is infinity or unbounded, you will not be able to apply classical measure. If your outcomes are not equally likely, then you will not be able to apply classical measure. Now, whatever questions you have seen for probability in this competitive exams and in 11th and 12th and so on and so forth, most of them were based on classical measure. So they went to counting. So you see over here, we are counting the number of outcomes in A. Over here, we are counting the number of outcomes in the sample space. So they went to permutations and combinations, right? So these are counting ways. So you can have counting, you can use these concepts of permutation and combination to count the number of outcomes in an event. And why did we find, so why did I find specifically this idea of probability difficult? Because I found permutation and combination difficult. So there were 10 balls, 3 are red, 3 are blue, and 3 are green. What is the probability of picking a blue ball? Over there we are implicitly assuming that all outcomes are equally likely, and obviously the sample space is not infinite. And they were testing us on permutation and combination, how well you are able to count. So what are the number of outcomes in A and what are the number of outcomes in S, and we just have to do this division and we are done. So that is what we were asked in those kind of questions. Okay, is this clear? So probability is not just about counting. So counting only comes when we are talking about classical measure. Sorry, when we are talking about classical measure. Frequentist measure doesn't have this permutation combination. Any questions? Okay. Then we'll move on. So there are some implications of this. So before going to frequentist measure, there are some implications of probability. Okay, so if you have probability of A, suppose this is some number greater than equals to 0. Now if I say probability of A complement, you can write it as 1 minus probability of A. How are we doing it? You see, probability of A plus probability of A complement will be probability of A omega, and we know that A omega, probability of omega is actually 1. Therefore you can say probability of A complement is 1 minus probability of A. Okay, there are other implications as well. So you see, when we talked about the third axiom of probability, if we go back, the third axiom of probability, probability of A union B, we found out it is probability of A plus probability of B. But this is the case when A and B are disjoint. What would happen if A and B are not disjoint? In that case, probability of A union B will be given by probability of A plus probability of B minus probability of A intersection B. Okay, so in artificial intelligence, this is known as inclusion-exclusion principle. Inclusion-exclusion principle. Okay, so this is one idea. What are we doing? We are just taking, so suppose these are the two events A and B. We are taking the probability of A, we are taking the probability of B, and you see we are double counting this part, so we are just subtracting this part. Okay, so this is all about this. Now we will move on to frequentist measure. Okay, and then we'll move on to conditional probability. Now you may ask me, why are we doing this? You see, take an example for suppose you are talking about a student, and that student is taking an exam. So he has studied for the exam. Now you can ask a question to that student, are you feeling prepared for the exam? Then after these two things are observed, you can say, did he pass the exam or not? And then did he celebrate the after the results of the exams were out or not? So these are the different outcomes, and each event in this experiment is dependent on the previous one. You see, so for studying, you just leave it out because that is the parent node. When we talk about whether the student feels prepared or not, it depends upon whether the student had studied well or not. This pass, so if you draw a tree, so for example this is studied, and this is dependent upon, so this you can say well prepared or not is dependent upon whether it has studied or not. Now this pass, this event pass, is dependent upon whether he has studied or not, or whether he feel prepared or not. Now whether or not he will celebrate or not, it will depend upon whether he pass the exam or not. So you see, you can draw a tree, and if you have probabilities of these kinds, so whether the probability whether the student pass given he has prepared and he studied is some number. Now with this probability you can have certain idea what is the probability that he will celebrate or not. So this is one case where multiple outcomes are included in an experiment, and all these different events are dependent upon one another. So this event is dependent upon these two events, this event is dependent upon this event. So these are compound experiments where one outcome of one experiment is dependent upon the outcome of another experiment. Okay, so this is one example where it is talking about a student. You can think about this as for example, weather predictions. So did it rain yesterday or not? Whether it was sunny in the morning or not? What is the wind temperature? So not what is the temperature? What is the wind velocity? And at last you will be able to conclude with some probability whether it will rain in the evening or not. Okay. So this is a tree you can create, and all these probabilities will give you some idea of the ultimate question you are asking. So this is the, so these probabilities are actually given. So these are the knowledge base you have. So whether it was sunny yesterday or not, with what probability it will be sunny tomorrow. So these are the knowledge base you will give, and you will want to ask a query whether it will rain today evening or not. So this is some kind of questions which will come. Okay. So where are we right now? We were talking about classical measure. What we will do is we will talk about frequentist measure very briefly, because it is not important to the concepts of AI, but I'll just cover it very briefly, and then we'll move on to conditional probability. The kind of probability we are talking about over here. What is the probability the student passed the exam given he prepared well and he studied? Sorry, given he feels prepared and he studied. Okay. So these are the things we will talk about. Okay. Any questions so far? All right, so it is 7 o'clock right now. We will meet at 7:05 and then we'll proceed. All right. And is this whatever we are discussing right now, is it all right, right? So I just want to have some idea. Am I able to convey the idea clearly, right? Okay. All right. Thank you. We'll meet at 7:05. So I hope you are back. Okay. So we were talking about frequentist measure. You see, previously when we were talking about classical measure, this is about counting of the number of outcomes in the sample space. This frequentist measure is different. What does it say is you perform this experiment multiple number of times and then you observe. So what is happening is, suppose you have a coin which is unfair. Okay, so you have an unfair coin. What it says is you toss the coin some number of times. It should be large number of times. Then you observe how many times did you have head. So suppose you had head n number of times, and what is the number of times you toss the coin? Suppose capital N number of times you toss the coin, then this will be the probability of occurrence of head. But this will only be that probability when this capital N tends to infinity. Okay, so it says that you perform this experiment infinite number of times, only then you will be able to converge to the probability of this head. Okay, so this is what frequentist measure is. It is actually the frequency of occurrence of that outcome you are interested in. Over here we are interested in heads. Obviously this measure also has some limitations. Before that, is this idea clear? What is frequentist measure? So suppose you are talking about um, um, again, so you have a unfair dice. Okay, and you want to find out what is the probability that a is equals to 1. So what is the probability that the die rolls a 1? So what you do, you roll the die capital N number of times, and you do this as many times as you can, and if n represents the number of times the die roll 1 and capital N represents the number of experiments you did, then this is the probability that die will roll a 1. Okay, so this is how frequentist measure of probability comes out. Okay, so is this all right? Now you saw some limitations of classical measure. What was the limitation? So these assumptions are becoming the limitation. First, if your outcomes are not equally likely, you will not be able to apply classical measure. Second was you cannot have an infinite or unbounded sample space, otherwise you will not be able to apply classical measure. There are limitations of frequentist measure as well. What are some of the limitations? You cannot perform this experiment infinite amount of time. You don't have that much resources. You cannot just roll the die infinite number of times, right? So this is one limitation. The second limitation is some of the experiments are costly. So suppose you have a new model of car and you want to find out what is the probability that the car will save your life given the safety features it has after a crash. So how many times you will perform that experiment? You will crash the car in infinite number of time? You cannot do that because some of the experiments are costly. You cannot just crash infinite number of cars just to find out the probability that it will save your life. Okay, so this is the second limitation. The third limitation is some experiments are actually impossible to perform. So for example, you are trying to find out the safety feature in an aeroplane, and you just cannot make some passengers sit in the aeroplane and then fly that aeroplane and you will see will that aeroplane crash or not. So this is one limitation, one more limitation, where some of the experiments are actually impossible to do. So this is an experiment which is possible, but some are actually impossible. So suppose there are some experiments on nuclear fission and you want to find out something, but you don't have the resources or it is impossible to do those kind of experiments. Okay, so these are some of the limitations of frequentist measure. So this concludes different measures of probability. Now we'll move on to the idea which is important for applications in AI. Is this idea clear of how do we measure probability? Okay, then we'll move on to conditional probability. So what is conditional probability? So you see, if you have some event A and you are saying this is the probability of occurrence of an event A. Now this probability might change depending upon what is observed, what you have observed. Okay, so these are known as evidence. You have some idea of this probability, but given some evidence you can update your probability. So take an example. Suppose there was a man who for his whole life lived in a cave. So he has never seen what is outside the cave. Now he comes out of a cave, of that cave, and then he sees there is light. Then his belief of world will be what? That I guess this light is always there. I'm 100% certain that this light will be there, right? Now when night comes, then the light goes out, there is no light. Then he'll update this probability. Maybe no, it is not 100%. Given that I see that there is no light, maybe this light will never come. So probability of A, given it is night, maybe it is actually 0%. That was a one time event. I saw light. Now there will be no light for forever. It will be no light. Or there is very less probability. So I can just say not zero. It is 1% chance that there will be light. He will be hopeful. I hope यार फिर से light आ जाए some way or the other. Then again in the morning he sees no, there is light. So he'll update this probability. Given some evidence, he's updating his probability. So this is what a conditional probability is. You have some beliefs of the world. Given some evidence, given something you see about the world, you can update your existing beliefs. Okay. So this is where the idea of conditional probability comes. So we'll take a toy example and then we'll see this idea going. So suppose the sample space is of two coin toss. So we can have head head, head tail, tail head, and tail tail. Okay. Now I say A is an outcome. A is an event which has head head and tail tail. Now I'll ask you what is the probability of A. So and all the outcomes are equally likely. So we are using classical measure. So what is the probability of A? Unmute yourself and you can just speak.
It's 1/2.
1 by 2, right? Now, this is when you don't have any outside evidence. So suppose you have some knowledge. What is the knowledge you have? Suppose I tell you that there is at least one head. This experiment occurred and there is at least one head in the outcome. So what are the feasible outcomes then? It will be HH, HT and TH, right? So these are the only three possible outcomes. This is the evidence you have. So someone gave you an evidence that there is at least one head in the whatever was the outcome of the experiment, there was at least one head. Now what you will do, you will update your belief. Your new event of interest will have A dashed will become head head, because you know tail tail cannot occur, right? You cannot have tail tail. Therefore, your new probability will be 1/3 and not half. Is this clear? So you see, what is this? This is actually probability of A given B. What was A? A was same outcome on both coin. Okay. What is B? At least one head. So this 1/3 is actually what? 1/3 is actually, you think about like this. You are just trying to find the probability of A given B has occurred. So in that case, 1/3 is the probability of A given B has occurred. And this conditional probability, it is written as probability of A and B by probability of B. It means what is the probability that both A and B has occurred by the probability of B. So you see, so what are the events both A and B can occur? So A intersection B, what is that event? You see, only head head can occur. So this is head head, right? And what is the probability of B? You see there are three outcomes, 1, 2 and 3. So probability of B, I'll write here, probability of B will be 3, by 4. You see the sample space has 4 outcomes, B has 3 outcomes, so it is 3 by 4. Probability of A union B, sorry, A intersection B. So what is probability of A intersection B? This is one outcome and you had 4 outcomes over here. So it is 1 by 4. So what is this? 1 by 4, 3 by 4. So 4 will be cancelled out and you will have 1 by 3. You see, this is exactly the same which we obtained by updating A to A dashed. So this probability is same as this. Therefore, probability of A given B is what? Probability of A and B by probability of B. Is this clear? In a similar way, you can have, yes.
Provided probability of B shall not be 0.
When you are saying that B is the evidence, but I don't think B will be, probability of B will be 0, right? Because that is the evidence you are observing. You are saying this has occurred. This is something you see.
Okay, yes.
Right? Because in that case, probability of A will be also 0. So suppose there is no outcome in B, then what will be A dash? A dash will also become 0, right? So it will be just 0. B is some evidence you see, and on top of that you are trying to say what is A dashed. So probability of B will not be 0 in such case. That cannot be an evidence. Okay, is it clear? Yes. So what is probability of B given A? So this will be what? Probability of A and B by probability of A. So you see, you can use these two equations because the numerator of both the equations are same. Therefore, probability of A times probability of B given A is equals to probability of A by A given B into probability of B. Is this clear? This idea? Because the numerators of both the equations are same, so you can just write like this. When you write like this, you can just do one more manipulation. You can write probability of B given A can be written as probability of A given B times probability of B by probability of A. Is this equation clear? Then I'll tell you the significance of this equation. Is this equation clear? Okay, so this is known as Bayes' law or Bayes' theorem. What it says is, suppose you have some kind of probabilities. What are the kind of probabilities? A given B and probability of B and probability of A, and you're interested to find out the probability of B given A, then you can use this theorem to find such probability. So for example, suppose you are interested to find out probability of disease given test result, test positive. What are you doing? You are saying that my test has arrived positive. So suppose COVID-19 test, and I'm saying that my test result was positive. I'm trying to find out what is the probability that I have the disease given I have a positive test result. I have knowledge of this kind of probabilities. Probabilities test result given disease. What does it say? What is the probability the test result will be positive given you have the disease? So this is what? This is efficacy of the test, right? Efficacy of test. It says that the test is 90% certain or maybe 80% certain will be positive. So if you have the disease, the test will be positive 80% of the time. So these kind of probabilities we have, and we are trying to find out this kind of probabilities, right? So we have such kind of probabilities. Another example I'll give you in artificial intelligence application. Suppose there is a sensor you have that there is some drone attack from in the air. So you see some missiles. You have a missile detection system. So you have this kind of probabilities that the missile system. So missile system gives positive given there is some missile in the air. Okay, missile in air. So these kind of probabilities you have because you have built the system. You know that if there is some missile in the air, this system which I have will be 90% of the time will give me positive result. It will tell me ki, haan, there is missile in the air, come on, do something. So these kind of probabilities I have. What are the probability I'm interested in? I'm interested in probabilities like this. Missile in the air. What is the probability that there is missile in the air given this equipment has given me a positive result? So this equipment is saying me that there is some missile in the air. What is the probability that there is actually missile in the air? Right? So we are interested in this kind of probabilities because this is important. You cannot ignore a positive response from the equipment. You have installed the equipment and you know there is some certain of the time it may be false alarm. You want to find out what is the probability that there is actually missile in the air given the system is being triggered. So these kind of probabilities you are interested in and you have these kind of probabilities. So in such cases, Bayes theorem helps you to find such kind of probabilities. Is it clear? Right? So you can have multiple such applications. Like I was talking about this face recognition system. So you have what is the accuracy of the system. So given my face, I know that, so given my face, I know 90% of the time the face recognition system will, it will find me, or no, sorry, it will detect my face. So given my face, this face recognition system will know that this is me. I am trying to find out the probability that if I show it a face and it is saying me positive result, whether it is me or not. So these kind of probabilities we are interested in, right? So did I make it clear to you or did I confuse you? Is it clear? Okay, so I assume it is clear. Okay, so let us see one example problem for this and then we'll move on. Okay, so suppose this is a COVID example. So suppose 10% of the people in the population has COVID. Okay, so this experiment is about whether you have COVID or not. So I'll say 10% of the time someone has COVID and 90% of the time someone doesn't have COVID, right? Now what I will do is I will perform the test. So I'll say positive, negative, positive, negative. So if you have COVID and this test is giving me positive, then we are saying what is the efficacy of the test. So I'll tell you that this test which we are doing, suppose some example I can give you. 90% of the time this test will give me a true positive result. There can be false positive as well. So this is false positive. So if you don't have the disease and the test is giving you positive, it can happen maybe. So let me take one example. I have one example. Consider the probability that false positive to be 0.02. So what is false positive? This is false positive. So this is 0.02, right? And false negative is 0.05. So false negative is 0.05. So this is 0.95 and this will be 0.98. Okay, so this is the probabilities. What it is? False positive. So given, so what is this probability? Probability of positive result given you don't have the disease. Given you don't have the disease, what is the probability of positive result? It is 0.02. What is this? This is actually false positive. So I know that 2% of the time this test result will be false positive. What is this? This is false negative. So this is what? Probability of negative given I have the disease. This is false negative. So 5% of the time this test result will give me a negative result given I have the disease. Okay, so this is false positive, this is false negative. Now what I want to do, you see I have this kind of probability. The test result being positive given I have the disease or not. The test result, so what is this? This is probability of being positive given I have the disease. This is what? Probability of the test result will be negative given I don't have the disease. So I have these kind of probabilities. What are we interested in? We are interested in what is the probability of having the disease given I have a positive result, right? So this is the probability we are interested in. How will we do that? We can do that by probability, just the opposite. Given the test result was positive, sorry, given I have the disease, what is the probability of having the disease times the probability of having the disease by probability of, just a minute, probability of A given B by probability of B, probability of the test being positive. So this is how we will obtain this probability. So you can ask me, how will we find this? We have this, we have this. You see, what is the probability of having COVID, which is 0.01. So this value I have, this is 0.1. This value also I have, you see, this is this value, which is 0.95. You can ask me, what is this value? So this you can use one more principle. So we talked about inclusion-exclusion principle. This one idea is there, marginalization. So this marginalization idea is from artificial intelligence. If you ask someone from the field of mathematics, the theorem which they will use is known as law of total probability. Law of total probability. And someone from the area of artificial intelligence will use the term marginalization. Okay, same concept but different names given by different person. So how will we get this? So you see, what are we interested in? We are interested in probabilities like this, probability of A. So here A I am representing as a positive. So how can you find this? You can just, so what are you doing? You are saying this is A. So what will we do is, we will divide it in different terms. We will say that I have an event B and this is B complement, right? So this is complete is B, this complete is B, and this is B complement. So what I will do is, probability of A is what? Probability of A and B plus probability of A and B complement. You see, these two events are disjoint. How? You see, we have divided it in between. So we are saying this is what? This is this area. Probability of, okay, this is this area. Probability of A and B complement, and this is this area. Probability of A and B complement. So we are dividing A into two parts. A intersection B and A intersection B complement, right? So we are dividing A into two parts depending upon what B is. And I'll show you how we will use this in this idea. So we are dividing the event A into two portions, A intersection B and A intersection B complement. So this will become, so you see we had this in conditional probability. Probability of A given B is what? Probability of A intersection B by probability of B. So you can just use this. So it will become probability of A given B times probability of B plus probability of A given B complement times probability of B complement. We are using this conditional probability. So this is known as theorem of a law of total probability or marginalization. Now how will we use this idea over here? You see, I have this positive test results and I can divide this in this part, COVID and non-COVID. So what can we do? We can just say this A is what? A is positive and B is COVID. B is COVID. So you just write this. So we'll have probability of, I'm just replacing A by positive. So probability of, over here it will be positive given C into probability of C plus probability of, this will be positive given not COVID, because I have B complement. What is B complement? Not COVID times probability of not COVID. You see, I have all these probabilities. I have this probability. What is this probability? Probability of positive given COVID, which is 0.95. What is this? This is 0.1. 0.1. I have this, which is 0.02. You see, this is 0.02, and this is what, 0.9. So I can obtain the denominator as well. I have all the numerator, so I can obtain this kind of probabilities. Now you may ask me, why are we doing this? You see, when we are talking about this problem, so we are talking about this kind of probabilities, right? What is the probability that the student pass given he felt prepared and he studied? So these are conditional probabilities, and you can use the ideas of the probabilities of these things, and then you can, so you can write an algorithm which can find you such kind of probabilities. Okay. And when I talk about this, these probabilities A intersection B, this is known as joint probabilities. So I'll tell you what this is. Before that, is this clear? What is Bayes' theorem and how can you find one probability given the other probabilities? Is this clear, or is it becoming too much to take in? Shall I proceed? Okay. Okay. So you see what we have talked about so far. So let us just summarize first. We saw basics of probability, like what is a sample space. Just a minute. Okay. So what did we talk about? We talk about basics of probability. What is a sample? So first we talked about what is an experiment, what is a random experiment. Then we talk about what is the sample space, then events. Then we talked about how to find probabilities, what are the measures of probabilities. Then we moved on to conditional probabilities. All right. Over there, using conditional probabilities, we saw Bayes' theorem. It helps us find the opposite of one condition. So if you are conditioning on one, it can give you the conditioning or the other. Okay. Now we can talk about joint probabilities, like probability of A intersection B. So this will be clear with an example. Okay. Before that, over here, A and B till now we were talking about is as events, right? But you can also have random variables. What are random variables? Random variables are, so I will not be technical because actually in mathematical terms, random variables are functions. But to be more clear, you can say, you can just assume random variables are variables that can take any value from a domain. Okay. So you can just say random variables are variables whose values are not fixed yet. So for example, you can say that the roll of a die, so that value which will it get, it can have a, it can be represented as a random variable. It can be either 1 or a 2 or a 3 or a 4 or a 5 or a 6. So that variable x is a random variable. What it does, it represents the face of the die. Okay, so this is one random variable. You can have other random variable as well. So whether a student passed the test or not, so you can have x take two values, pass, not pass. Generally random variable takes numerical values, so you can just replace pass and not pass by 0 and 1. Okay, so random variables generally take, not generally, it always takes actually numerical values. Okay, so you can have other things also. So what is the temperature of tomorrow? So it can be any number, right? So that is a random variable. So random variable generally take numerical values. Now you can have two random variables. One is, suppose, the rain in centimeters, and another you can have y as, suppose, temperature, right? So you can have rain in centimeters and temperatures. These are random variables. X represents the rain in centimeters and y represents the temperature in Celsius, suppose. So you can have probabilities like this. What is the probability that it rained, suppose, 20 centimeter given y was 30 degrees centigrade? So these are also probabilities. What are you trying to say? So what is the probability that it rained, suppose, more than equals to 20 centimeter given the temperature was exactly 30 degrees centigrade? This kind of probabilities also you can find. You can have, so this is conditional probability, right? Because your condition on one more event over here, that is y is equals to 30 degrees centigrade. So these are conditional probabilities. Another can be joint probabilities. What is joint probability? So it is just x greater than equals to 20 centimeter intersection y is equals to 30 degrees centigrade. So these kind of probabilities are known as joint probabilities. You are fixing both x greater than 20 and y is equals to 30. Conditional probability is what? This joint by probability of y is equals to 30 degrees centigrade. So this is what a conditional probability is. Joint probability is just the numerator. So I'll take one example and then it will be more clear. Let me go, I have some examples. Okay, so this student example. So suppose there are two conditions. Let us say that student studied and not studied. So I'll just like write this not studied, or I could just write a complement as well. Okay. So what is the probability the student studies? Suppose it is 0.4. And what is the probability that the student did not study? It is 0.6. Another, so this is one kind of random variable x, which takes two values, 0 and 1. When it takes 0, it means the student studied, and when it takes 1, it means that the student did not study. Another random variable, which is y, it says that let us take the student passed the test or not. Okay, so it is pass. So suppose when y takes value 0, then it means pass, and not pass means fail. When y takes a value of 1, then it is fail. So suppose the probability of pass is 0.1. So these are just made up numbers. It may not mean anything. And not pass is 0.9. So these are individual probabilities. So when I say probability x is equals to 0, which is equals to 0.4, you see there is no condition on y. Or when I say probability y is equals to 0, which is 0.1, there is no condition on x. But you can condition on x, which we have seen, conditional probabilities, right? There can be joint probabilities as well. So we'll talk about condition and joint after I give you one table. So suppose this is the table. So it will have x in one column and y in another column. So this is x is equals to 0, x is equals to 1. I'm not writing studied, not studied. You just interpret it in that way. Y is equals to 0 and y is equals to 1. Okay. And these are the numbers 0.08, 0.02, 0.32 and 0.58. Okay. Now you see, what is this? What is this? This is what? This is probability x is equals to 0 and, so I'm writing intersection. You can just write like this also, and sorry, not like this, like this, and y is equals to 0. It means probability the student studied and passed the test, which is what? Which is 0.08. Okay. So this is joint probabilities. You are specifying the values of two random variables at once. Probability of x is equals to 0 and y is equals to 1, which is 0.32. Okay. So this is what joint probability is. From joint probability, you can calculate conditional probability. So for example, you are interested to find out probability x is equals to 0 given y is equals to 0. What is the probability that x is equals to 0 that and given y is equals to 0? So you see, when y is given, so what is this? Probability of x is equals to 0 and y is equals to 0 by probability of y is equals to 0, right? This is what it means. This is we have seen when we are talking about conditional probability. You see that numerator, I know. What is the value of the numerator? The numerator is 0.08. Denominator I have to calculate. So what is the probability of y is equals to 0? We know it is 0.01, but you can calculate using this joint probability as well. You see, you add these two ups because this is the condition where y is equals to 0. Y is equals to 0 for this, and if you add this up, it will become 0.1. And you can calculate this kind of probabilities. Probability x is equals to 0 given y is equals to 0. Is this clear? Is this clear? And this marginalization will also work over here. So we're talking about marginalization. So over here you see where is space? Okay. So probability y is equals to 0. You can use marginalization. So what I did here, you see, when I was talking about probability A is equals to what? Probability of A and B plus probability of A and not B. So you can do that over here as well. Probability of y is equals to 0 and x is equals to 0 plus probability of y is equals to 0 and x is equals to 1. So because x is equals to 0 and x is equals to 1 are complement of each other. So you see it is what? 0.08 plus 0.02, which is 0.1. So you see this is what? Marginalization. When we are adding over here to find probability of y is equals to 0, we are doing marginalization. Right? So we have talked about three important things right now: joint probability distribution, conditional probability distribution, and the ideas of marginalization and Bayes theorem. Those are important concepts which we'll use. So I hope you have got the idea of joint distribution. Any questions on joint distribution? Okay, if you don't have any questions, please find out probability y is equals to 1 using marginalization. So you know actually it is 0.09, but use marginalization, write this equation of marginalization, and then try to find out if it is equals to 0.09 or not. What is marginalization? You see what we are trying to do. We are trying to say probability y is equals to 1. What we will do is we will include one more variable inside it. So we'll say probability y is equals to 1 given x plus probability y is equals to 1 given x complement. When we add these two things, this is known as marginalization. Over here we will say x is equals to 0 and x is equals to 1 because those are complement of each other. Okay, so do this and you see if it is 0.9 or not. Okay, so I hope you could do it. It will be probability y is equals to 1 and x is equals to 0 plus probability y is equals to 1 and x is equals to 1. So this is what? This is 0.32. So it will be 0.32 plus 0.58. So it is 0.58. When you sum this up, it will become 0.9. So this is, you see, this is same as probability y is equals to 1, right? Is this clear? Now you see over here we did marginalization into two. So we divided y into two components. We could have divided it to n number of components. So when I say y is equals to 1, this could have been divided into n number of components. So probability y is equals to 1 given x takes some value, suppose it is 0, plus probability y is equals to 1 comma x takes 1, plus probability y is equals to 1 comma x takes some other value plus dot 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 dot. But you have to do it until all the values of x are taken care of. You cannot leave out any values of x. So you can imagine this, for example, like this. So this is y, right? And this is another event. So I'll just take another color. So what are we doing? We are dividing. So I'll just erase y. So suppose this is y. Okay, inside one is y. What are we doing? We are dividing x. So this is x one value, this is another value, this is another value, this is another value, and so on and so forth. So this is x is equals to 1, x is equals to 2, x is equals to 3, x is equals to 4. But you have to add everything. Why? Because each time you are taking this part, x is equals to 1 and y is equals to 0. So x is equals to 0 and y is equals to 1. So you are talking about this part. Then when you are saying y is equals to 1 and x is equals to 1, you are talking about this part and this part. So for getting the probability of y is equals to 1, you have to sum all the components. You cannot leave out any component, right? So for all values of x, you have to sum, then only you will be able to get probability y is equals to 1. Is this clear? Now, if you think about it, these are joint distributions, and we could also use conditionals. We talked about this over here. So when we have this kind of A and B, you can convert it into conditionals. So these are ideas I am giving you. So if you don't have access to this kind of values, you can get those values by conditioning. So for example, suppose you have a network like this. So this is the parent, and this leads to two values. Suppose, so for example, we're talking about that student example, right? So this is studied or not, feels prepared or not, and for this it will come down to pass or not, and then celebrate or not, right? So the probabilities which you will have access to are like this: probability pass given the student had studied and the student is prepared, feels prepared. Probability that the student feels prepared given he has studied. So probability, because this doesn't have a parent, it will be probability the student has studied. What will be this? This will be probability the student celebrate given he has passed. Okay, so you will have access to such kind of probabilities. Now I'll ask you, so some evidence you have obtained, like I told you that the student has studied. So I'll just say like this: S is equals to true and P is equals to false. And I'll not talk about anything about past. I'll ask you what is the probability the student celebrate. So you have to find. So I'll tell you that the student has studied, which is true. The student does not feels prepared. The student is not feeling prepared, which is false. Obtain the probability that the student celebrated. So this probability you have to obtain from this network using all the ideas which we talked about earlier. So this is what, this is actually inference. You see, you have a network, you have some knowledge of the network, and you are asking a question whether the student will celebrate or not. You will not be able to tell me with certainty that 100% I'm sure that it may be 100%, it depends upon the network, but there is some uncertainty which will be manifested in this network. So this inferences which we are doing in this network is dependent upon the probability of other events which influence this. So for example, you have sent a robot in Mars and it observes some, takes some images and observes those images. It will come to a conclusion that yes, this is a object which is a rock. It will be uncertain. It has taken some data. It depends upon some so it depends upon the accuracy of the sensors it is using, and then those conditions will come, and then it will be given that yeah, it seems to be a rock with I am this percent sure, something like that. So for example, this GPT which we are seeing right now, when you type something to this GPT, this GPT doesn't have that is it is not 100% sure what you're talking about. It takes the network, it builds the network, it takes the input from you, and it says that I am 95% sure this person is talking about these things. I should give this answer because it has more chances to be correct. It has 95% I'm certain that this is correct. So it builds multiple solutions. It has some solution which is he is 50% sure. It builds another solution which it is 70% sure, and so on and so forth. So whichever solution he is more confident in, that solution will be produced to you. So something like that is occurring inside that also. Is this idea clear? Okay. So the last concept which in probability which we'll talk about is independence. Two events A and B are independent when probability of A and B becomes probability of A times probability of B. When this occur, then you can say that the probability that event A and B are independent. So take an example. So you know, just a minute, I'm sorry. Okay, so we know that probability of A and B, or you can say intersection B, is given by probability of A given B times probability of B. Now you see, when I say A and B are independent, I am saying that this, obviously the left hand side are the same. So we are saying that probability of A, this thing, into probability of B is what? Is this, which is probability of A given B times probability of B, which means probability of A is equals to probability of A given B. What does this mean? It means that occurrence of B did not influence the probability of A. That is, whether or not event B occurred doesn't influence the probability of occurrence of A. Therefore, A and B are independent. And you can also do that by saying probability of A intersection B is probability of B given A times probability of A. Now in the second case, it will become probability of A times probability of B, which will be probability of B given A times probability of A. A will be cancelled out, and you will be able to see that occurrence of A did not influence the probability of B. So this probability is same as this probability. Therefore, probability of B did not change if A occurred. Therefore, A and B are independent events when both of these conditions occur. So these both conditions are actually taken care of by this expression. And therefore, in such conditions, we say A and B are independent. I'll give you one example. So this is a very good example, by the way. Is this clear idea of independence? Okay, so suppose we are tossing two coins. So head head, head tail, tail head, and tail tail, right? Now I say event A is what? Event A is head head and tail tail. The probability of A will be half, right? Now if I give you B, which is what? Which is at least one head, which is head head, tail, and head tail, right? So we saw in such cases probability of A given B became 1/3. You can go back and see. Otherwise, you can just do like this. What the concept which we learned. It will be probability of A intersection B by probability of B. So what is probability of B? Probability of B is 1/3, and probability of A intersection B. So what is A intersection B? A intersection B is just head head. So it is 1/4. Just a minute. Probability of B 3/4. Yeah, sorry. Probability of B is 3/4. So this will be 1/3, right? Now, instead of this, suppose I say there is an event C, which is head head and head tail. The first toss word head. So what is B? B is, I'll write it. B is what? B is at least one head. What is C? First toss is head. So in such cases, you see what will be A intersection C. A intersection C will be head head, right? Now when you calculate probability of A given C, you will have probability of A intersection C by probability of C. What is probability of C? Probability of C is half. Probability of A intersection C. Probability of A intersection C is actually 1/4, right? So it will be 1/4 by 1/2, which is actually 1/2. So you see, probability of A was 1/2. Probability of A given C is actually 1/2. Therefore, A and C are independent. You see, actually, occurrence of C did change the event A. You see, it is actually terminating this outcome. It is saying that this outcome will not occur. Because of C, some of the outcomes of A are actually getting terminated. It is actually getting impossible. Then also we are saying A and C are independent because this condition is getting met. Probability of A intersection C is same as, so you can just check probability of, probability of A intersection C will become probability of A times probability of C. So you just do what is A intersection C. A intersection C is 1/4. Probability of A is half. Probability of B is half. So it will be 1/4 is half times half. So you see it is becoming equality. Therefore, A and C are independent. Although occurrence of C is actually eliminating some outcomes of A, then also we are saying A and C are independent if this condition is met. If this condition is met, then we'll say A and C are independent. Is this clear? Is this clear? All right, so this is everything. Yes, yes.
uh, in the instant example, when you say that, will you please, yeah, sample, when shall I define a set A as a set of outcomes with same
Yes,
phase
yes.
is
Same
HH,
face, same face.
correct? And event C, as we can see, is a event
First toss
first
is
phase
head.
is head.
First toss is head. Yes.
First phase is head. So A and C have have one common element, that HH.
Yes.
So in this case, A intersection C 1 by 2 into 1 by
What?
2.
Just a minute. Just a minute. What is A intersection C? What is A intersection C? A intersection.
Probability of A into probability of C
No,
for
no,
independent events.
no, no. From classical measure, it will be the number of elements in
The
A
number
intersection.
of outputs of A intersection be upon sample space,
So
correct?
it what? So it is 1/4, right?
Yeah.
Now probability of A. What is probability of A? You see, probability of A is half.
Okay, yeah.
Probability of C is also half.
Hmm.
So half times half is 1/4.
Okay, that's true, but probability of, okay, ठीक है, okay.
Actually, this independence idea is not upon if it is eliminating some.
If I'm not wrong, independent events, we must define occurrence of one event does not affect the outcome of occurrence of another event.
Probability, not outcome. Probability. Occurrence and non-occurrence.
Probability depends on the outcome.
No. You see, independence is actually defined upon probability. Occurrence and non-occurrence
The
of
reason,
one does not change the probability of the other.
the reason behind this statement is probability of occurrence of first head doesn't affect the probability of occurrence of probability of occurrence of outcome with same phase.
No, you see, when I'm saying C occurred, means first coin is head. You see, the second outcome of A is getting eliminated. Therefore, occurrence of C is actually eliminating some outcomes of A, right? When I'm
Okay,
saying
okay, yeah. Probability, if probability of occurrence doesn't affect, then it's okay. Yeah,
yes,
accepted, accepted.
yes, that is what I am trying to convey.
Okay, okay, okay. Yeah.
Okay, and one last comment. So whatever I have taught about probability, I have actually followed our department's curriculum, and this whatever I have taught is taught by my guide, Dr. Abhijit Khandra. So this is all from his notes. So I am very thankful to him to have taught this subject to me, probability and statistics. So whatever I am teaching you right now has come directly from Dr. Abhijit Khandra. Okay, so this is it. I have posted today's assignment. You go through the assignment, and we will not have a next class on next Sunday. Our next class will be on 3rd of November, if I am not wrong. I'll just check and tell you. I'll post it in the group as well. Yes, 3rd of November. Okay. If you have any doubt or so, you can just tell me. But the assignment submissions deadline is next Sunday. So submit the assignment before next Sunday. And each assignment which I give you will cover each module. So the first assignment which I gave you was on search. The second assignment I gave was on logic. Since we just talked about introduction to probability, so I don't have any assignment for this uncertainty, but when we cover the actual concepts of those uncertainty, then we'll have one assignment on uncertainty as well. This way you will be able to cover each and every concept with an assignment. Okay, and I'll have few more classes on introduction to Python, because there are few students who are yet to have good grasp on Python. I hope you're enjoying the course. Please give me some feedback to improve or so. Thank you. So if you don't have anything to add, you can just leave the meeting. I'll just end it now.